Have you ever wondered what happens when things change? Like when a rusty nail appears on an old bike, or when you strike a match and, fire? That's chemistry in action. It's all about substances changing into new substances. To describe these amazing transformations, scientists use a special kind of recipe called a chemical equation. Think of it like a recipe for a cake. It tells you what ingredients you start with, which we call reactants, and what you get at the end, which we call products. It's a shorthand way to show a chemical reaction. Consider it. Now here's the cool part. These chemical recipes have one very important rule. You can't just throw things together and hope for the best. There has to be a balance. Imagine you're building something with Lego bricks. If you start with 10 red bricks and 5 blue bricks, you must have 10 red bricks and 5 blue bricks somewhere in your final creation. They might be clicked together in new ways, but they are all still there. Chemical equations work just like that. Balancing them means making sure you have the exact same number of each type of atom on both sides of the recipe. This idea of balancing is super important. It's not just about making the equation look neat and tidy, it's about following a fundamental law of the universe. When we balance an equation, we are showing that we understand that matter, the stuff everything is made of, can't just appear out of nowhere or disappear into thin air. Every single tiny atom we start with must be accounted for at the end. It's like being a detective for atoms, making sure none of them escape the scene of the reaction. It's a core principle of science. Science! So why do we take the time to do this? Because a balanced equation gives us incredible power. It allows us to predict exactly how much of a product we can make from our starting ingredients. This is crucial for everything from baking a perfect loaf of bread, to manufacturing medicines, or even figuring out how much fuel a rocket needs to get into space. It turns a simple description of a chemical change into a precise, quantitative tool that scientists and engineers use every single day to build our world. It's pretty amazing when you think about it. To really get this, let's zoom in. Way in. Everything around us, the air you're breathing, the screen you're reading this on, is made of tiny particles called atoms. Atoms are the basic building blocks of all matter. Think of them as individual letters of an alphabet. There are different kinds of atoms, like hydrogen, oxygen, and carbon. These are the elements. There are over 100 different types of these atomic letters in our universe, each with its own unique properties. They are the fundamental ingredients for everything. Now, what happens when these atoms get together? They form molecules. A molecule is just a group of 2 or more atoms stuck together. If atoms are letters, then molecules are the words they spell. For example, a molecule of water isn't just one thing, it's made of 2 hydrogen atoms bonded to 1 oxygen atom. We write its formula as H2O. The little 2 tells us there are 2 hydrogen atoms. A molecule of oxygen gas, the stuff we breathe, is made of 2 oxygen atoms bonded together, so we write it as O2. Molecules are everywhere, making up almost everything we interact with. This brings us to a huge, very important rule in science, the law of conservation of mass. It sounds complicated, but the idea is simple. It just means that in any chemical reaction, matter is not created or destroyed. The total amount of stuff you start with must equal the total amount of stuff you end with. The atoms just rearrange themselves to form new molecules. They swap partners like dancers at a ball. No new dancers join, and no dancers leave the ballroom. They just find new partners to dance with. This is the law we must obey when we balance equations. So when we see an equation like H2 plus O2 makes H2O, we have a problem. On the left side, the reactant side, we have 2 oxygen atoms in the O2 molecule. But on the right side, the product side, we only have 1 oxygen atom in the H2O molecule. One of our oxygen atoms has vanished. This breaks the law of conservation of mass. It's like a dancer disappeared from the floor. Our job as science detectives is to fix the equation so that every atom is accounted for, ensuring our chemical story makes sense and follows the rules of the universe. Alright, let's balance that equation for making water. H2 plus O2 makes H2O. It looks simple, but as we saw, it's unbalanced. Let's fix it step by step. The first step is to draw a little inventory table. Make a list of all the atoms on the left side, the reactants, and all the atoms on the right side, the products. For our equation, the list is simple, just hydrogen and oxygen. This helps us keep track of everything so we don't get lost. It's our scientific scorecard. Now let's count the atoms. On the left side, the H2 molecule gives us 2 hydrogen atoms. The O2 molecule gives us 2 oxygen atoms. So our starting inventory is hydrogen equals 2, oxygen equals 2. Now look at the right side. The H2O molecule has 2 hydrogen atoms and only 1 oxygen atom. Our ending inventory is hydrogen equals 2, oxygen equals 1. We can see the problem right away. The hydrogens are balanced, but the oxygens are not. We have 2 on the left and only 1 on the right. We need to fix this. Here's the key trick to balance the equation. We can only change the big numbers in front of the molecules. These are called coefficients. We can change the little numbers, the subscripts inside the molecules, like the 2 in H2O. Changing that would change the molecule itself. H2O2 is hydrogen peroxide, not water. So to get 2 oxygens on the right, we must put a big 2 in front of the H2O molecule. Our equation now looks like this. H2 plus O2 makes 2H2O. We are changing the number of molecules, not the molecules themselves. Now we have to recount everything. The left side is still hydrogen equals 2, oxygen equals 2, but the right side has changed. The big 2 multiplies everything in the H2O molecule. So now we have 2 times 2 equals 4 hydrogen atoms and 2 times 1 equals 2 oxygen atoms. Our inventory is now hydrogen equals 4, oxygen equals 2. Look, our oxygens are now balanced, 2 on each side, but we've unbalanced the hydrogens. That's okay. Balancing is often a back and forth process. To fix the hydrogen, we go back to the left side and put a 2 in front of the H2. Our final equation is 2H2 plus O2 makes 2H2O. Let's do a final count. Left side has 2 times 2 equals 4 hydrogens and 2 oxygens. Right side has 2 times 2 equals 4 hydrogens and 2 times 1 equals 2 oxygens. Everything matches. It's balanced. When you're just starting, it can feel like a puzzle. One common mistake is changing the small subscript numbers. Remember, you can't do that. H2O is water. If you change it to H2O2, you've made a completely different substance.